some bit of a background noise somewhere. Your end, Paul?
Yeah, I hear it too.
Uh-huh. Okay. So, sorry. Is it your end? Is it Paul? Okay. No, no, no,
No,
no, no,
the
no, no.
the the machine
There's
the
a sound.
machine voice.
Yeah.
The machine, yeah. It,
Okay.
again,
That,
it's
that, well, I'll blame Romit because he's the nearest person to the airport.
Oh, okay.
Okay, so in this case over here, so you can see how one of the edges is a long edge.
Mhm.
Short edge. So with the two-way slabs, this is our worst case when one of your long edges and the short edges are not continuous, which means there's nothing on this side and this side. So there's nothing over here. There's nothing over here. Then we've got our two short edges, which are continuous, and one long edge, not continuous. Then then we've got all the edges which are continuous. So this one over here is our best case scenario. Does it make sense?
mm-hmm.
And then this one over here has got our short edge discontinuous, and all the other three edges are continuous. So, but the reason why this is the worst case is that there is no moment distribution in the actual slab. So what happens is that the moment is not. So if I draw a cross section of the slab, don't mind my sketches. What is it doing that? Stay with me for a second. Okay. So what happens is, if we're looking at a simply supported beam, then our moments are like that, isn't it?
Yeah.
So as soon as we go towards the end, we tend to have zero moment. In reality, with concrete structures, there is some moment over here. It's very small though, but you do have some moment. So that's how, because it's one piece, and being an in situ construction, it's monolithic, so it's one construction. So there is some moment transfer, but a lot of the moment is transferred over here at the supports, and that's what's helping the beam or the slab to work and be more efficient because it transfers the moments from here to there and goes down across and so forth. So if this is sort of a representative cross section to here. Makes sense? I'll just label that X. So in a similar way, what happens is the slab actually transfers the moment to this side over here and this beam over here. And in a two-way construction, the formulas which are coming from the code, just stay with me for a second. I'll just copy the code across. You guys are on page 87.
Yes.
So that's the formula which tells you how to design the moments for each section. Your LX is your one of the lengths, and BX and BY are the factors. If you go to the next sheet, is based on that table 6.1, 6.10. Does it make sense? Can you see the table? It's on page 88. I'll just screenshot it over here. So if you can see this.
Yeah, that's 89 in the Dropbox.
89, is it?
Yeah.
Okay, that's surprising. My one is saying 88. Okay. So you guys are looking at 2009 code?
Yep.
Oh, yes.
Really? So you got the new one. Okay. So maybe you can share that with us. And is it in the Dropbox? Okay. All right. So I must have got the old one. I just
The one
picked
that
up
I'm
the
looking at is 2009.
2009.
Yeah.
3600. Yeah. So 2009 is in the folder. And so where is it in Dropbox? 3600 link specification. I can't see that. Only AX code. Yeah, all I can see is but anyway, that's right. So it's similar. I don't think the factors would change. So based on your LY/LX, you can get your factors of for 4 edges continuous, 1 short edge, 2 short edge, and if you were to do a hand computation, this is how you can design these more using all these formulas. You can get your moments over the support. Makes sense?
Yep.
You guys with me, Kelvin and Robert?
Yes.
Yep.
Yes.
So just going back to Toolkit, Toolkit has done that for us. And if we know what it is, you've got long edge, which is LY, short edge is LX. So I've done it for usually at a typical raft slab, which could be 4.5 meters by 4 meters. That's looking at a worst case. Usually our edges would be 4 meters by 4 meters max. But just for the sake of the exercise, 4.5 meters by 4 meters. Our typical slab thickness of a raft slab, if it's suspended, is 130. Self weight is already included in there, and I've just put 0.5 as superimposed dead load. So superimposed dead load could be your tiles, your timber flooring, and things like that. I'm just being a bit conservative and putting 0.5. It could be less than that. And live load is typical, which is it's standard for a residential type construction. If you were checking this for a garage, then this would change to 3 kPa. Maybe. Why am I doing this? Should probably use my notes and things. Garage. Then so when we go to the next section, it does all the analysis for us. You can see how they've got your BY, BX, and your alpha values, and then it calculates your moments over the support.
Mm-hmm.
It also gives us a diagram, which is continuous, which is not continuous, and gives you some sort of support moments along the discontinuous edge. If you still attract some moments there, but it's 50% or less of the moments over here.
Mm-hmm.
So when we are checking our slabs, the critical moment is this moment over here, and all this moment over here, because that's the one which is deflecting our slab. The moment across over here is critical, and I'll show you what I mean by critical. So the spreadsheet does a lot of the analysis for us. So when you look at the computation you were doing the other day, Romit, with your fully suspended slab on piers, or it could be fully suspended on blinding concrete. This is what we should be doing to check if we can, if our slab is adequate. So sometimes, once we've done a slab of 4x4, which is the worst case situation, we know that all the other slabs will work. If something in the middle of the slab is 3.5 by 5 meters, we know it will work because the worst case has worked, and we all have to do this once or twice in our lifetime to have that confidence that this is how that's how the slab behaves. This is how the moments are distributed, and I've done it once, and I know that a 4x4 slab works. Is it right? It's like building a confidence. Like, see, for example, if you've done a steel column check, and roughly the capacity of a steel column, 89 by 89, we don't have to do that all the time.
Mm-hmm.
Once you've done it, you know how to do it, and most of the time in a small construction, like a 2-story house, it works. Even if it supports a 360 UV and it's 7 meters long, we know that it will work. But as soon as you are putting a 500 UB, something like that, then it would prompt you to check the column because the loads are a lot higher than normal, what you would normally use.
Yep.
Make sense? So in a simple this calculation will do the same too. Then we move down to the next one, which is deflection. So this deflection, this one over here only checks the deflection. It doesn't check your strength. And how they check the deflection is based on the minimum thickness of the slab based on the reinforcement you have provided. With any members, the effective D is the most critical bit. It could be steel, it could be timber. The effective D is the most critical thing. So so this is what they're doing. Based on the D, they know that this slab will work in deflection. If I'll show you something else. Can you guys find out a simple slab? Section is just a normal slab. In the code, I'll find it out for you guys. There's a section which talks about the minimum D for your deflection. They've got some formulas. So for a one-way slab, you've got a formula which calculates your minimum D. I don't know.
I have something. I'll just send a screenshot on Teams.
Oh, okay. So you when you guys were doing your concrete unit, you would have seen that. I don't know if do you recall that, Kelvin?
The concrete unit.
Yes, it's a formula which gives you an effective D.
Yeah.
It's sort of based on the length of a member, and so it's length divided by a number. It could be 180 or 250.
Yep.
And it gives you a rough D. Yeah,
Yes.
and then from there you do the actual calculation of your slabs.
Yeah. I think I have it. Just give me a second. I got this book from the library. There wasn't any other copy except for one copy. So
you stole the book?
I had to take pictures of 600 pages.
Yeah, I think we've got not sure if we've got a concrete book on the server, but there should be something. Have you guys heard of the book called Warner Rangan and Hall? There's one in the office. Concrete.
I think I have that book.
You've got Warner Rangan?
The soft copy.
Okay. So yeah, Warner Rangan is good. For 1 second, I'm finding. But yeah, that's
the book I'm referring to. The one I got image from the library.
Oh yep. Okay. So yeah, it's a good book. Yeah, it's very it's got good design guides.
Yeah.
Very, very good design guides. So okay, well, you guys can share that information a bit later. I thought I'll just give you a guidance of what the D does. So once we've got all these moments, then you will be thinking, how do I calculate check the capacity? And one is you can do it either by hand, or you could go to toolkit. and then you go to your member design. I'll share the screen also so that you guys can see. Yeah. Okay. So let me know when you guys can see the screen.
Yeah. I've sent the image.
Okay.
Yeah.
See the screen. Okay. Yep. So yeah. So this is one of the formulas which get you to look at the total thickness of slab. Yep. I don't know. I'll put it in here. Let me just. Sorry, guys. I'll put it on Bluebeam, and I'll share this file. So once we've done, I'll share this file with you guys. Okay. So we go to our analysis, and I'll take that to 25 MPa, and that to and 130 is the minimum. And the reason being is give me 1 second. So we scroll down and we look at our moment. So usually when we're doing an analysis, we'll be do an analysis in here. We put in all our loads, and that's how we actually get all our designs, isn't it? It says say 0.5 and 1.5, and that's say 4 meters, and say external. For this one over here, it's a one-way slab analysis. So it's just a very approximate way. It's not as accurate as full analysis in toolkit or space gas or something like that. But by looking at the diagram, you can see how a one-way slab behaves, isn't it? Can you see?
Yes.
We designed it as a one-way slab. Can you see how the positive moments are 8.6?
Mm-hmm.
And is minus 11, close to minus 11. High. So the negative moment is almost 50% higher than a two-way slab analysis, and the positive moment is twice, more than twice. So if we're using a one-way slab and with a span of 4 meters, a 136 slab will not work. And switch to design, and our mesh is usually SLAD2. You can see how it's failing. It fails in strength. and it fails in cracking. We know that the analysis is not correct, but just for the sake of the exercise, you can see how if we were designing it as a one-way slab, a 136 slab will not work. If I make this into a 156 slab, it still doesn't work. And the reason being is that our reinforcement is not big enough. So I'll increase this reinforcement and let's make it to say SL81. And we can see that the slab worked. And it works with minimum reinforcement. It's got enough ductility, and the strength is quite good, so it works. Let's go back to our 136 slab with our SL82, and then we go here and we type in manual. So this is where we put in our moment. So if I put in from 9, my negative moment was minus 7.8. So I'll put this as minus 7.8, and I'm checking my negative moment, and so yeah, it's saying that it's failing. My slab is failing. And I wouldn't worry about that. The reason being is, if I'll switch my screen again. Okay. Can you see my screen?
Yep.
Color pen. If we have a look at that, my 7.8 is over here. What the software is designing it is based on that D. And the way it's designing it is, we've got reinforcement over here. So the blue line is my reinforcement. Can you see that? And so the effective D is the software. Structural Toolkit is taking your effective D from here to there. There is that distance. But in reality, your effective D is there, isn't it? Makes sense? So, and our moment, the most critical moment is sort of, so that's the moment which we are looking for. Does it make sense? So if the moment at this section over here is more than 7, then we know that, okay, my sled is failing. You can see how exponentially it drops quite rapidly, isn't it? At this location, we would know that my moment would be less than 7. Go back. Yep. At that location. Does it make sense? Or if we go and have a, I'll switch screen again, so just to show you on toolkit. Are you guys following what I'm saying, or?
Yeah. Yeah.
Yes.
It's a bit hard when you are doing it like this. So you can see how that's 3 meters. Can you see my screen?
Yeah.
6, 7, 8, 9, 10. Okay. So it gives us an increment of 100 mil. So from there to there, roughly, our beam is roughly 1. It's 1.4, isn't it? Sorry, 300. So from the center line, it's 150. So your moment at 150 would be, going back, is 10, 150. So your moment would be roughly around, I would say, 7.5, isn't it? Can you see that? So, and in a similar way, you will see something similar happening to your two-way slab too. The two-way slab is more forgiving because there's more distribution. It distributes it in both directions. That's the reason why in a normal raft slab, I'm not worried about the negative reinforcement or the negative moment. Because we've got a deep beam there, it doesn't, when we put it in the normal analysis, it doesn't give us the correct answer. So if I want to cheat a bit and say, okay, I'm gonna have that as 150 thick. If I make that as 150 thick, my slab works, isn't it?
Yeah.
That's cheating. But in reality, my effective D is 400 at that location.
350 to 400.
Yeah. So it's about 4. Sorry, my total depth is 400.
Yeah.
So you can see how our capacity has increased by quite a lot. So I'll just change this to 130. And then I'll make this into 4. So 4 is my positive moment, which, when we looked at this, so that's my positive moment, which I put into here. So this actually gives me the design here. So now you can see by designing it as 136 slab, a 4 kilonewton moment works quite well. So we should be fine. If you're designing a two-way slab, that's looking at the worst case. What we can also do is, if we go to the analysis in here, sometimes we have point loads in the middle of the slab. So we've got dead and live point loads, and we underneath those point loads we put a pad footing. So in a two-way slab, what we can also do is, if we've got a dead load of say 2 kPa, sorry, 2 kilonewton. So 2 kilonewton divided by 4.5 by 4 gives us a kPa value, isn't it? Let's make it higher. Let's make it say 5 kilonewton of dead load, and live load is say 5 again, to make things simple. 5 divided by 4. 0.28. So I've got a distributed, like an equivalent pressure applied to the slab, which is 0.28 kPa. Are you guys following me?
Yes.
Mm-hmm.
So what I'll do is, in my analysis, I'll make that into 0.8, and I'll make my live load as 1.8. So I have added that 2.28 or 0.3 kPa into my superimposed load and my live load, and then it gives me a see the moments down over here. So now it's gone to 4.5, 4.1, 8.8, 9.3. Can you see that?
Yes.
So what we can do is the idea why I'm explaining this to you guys is that when we have a suspended slab system, especially on board piers, we with board piers it's expensive to have multiple board piers underneath the slab point load. If which is going down 600-700, it's not too bad. You can dig that and put it in there. If you've got small, you can distribute these small loads within your slab, and it reduces the amount of concrete. You don't have to worry about putting board piers or things like that. In most cases, that would be your one of your edges, and it's usually two edges continuous. In my experience, I've hardly seen your point loads, the smaller point loads closer to the edge, external edge, isn't it? It usually happens where you've got your stair voids and your little trimmers, which happens to be in the middle of the slab.
Mm-hmm.
Not on the not closer to the outside, isn't it? So in most cases, and Paul did something like this the other day for Milne? Mills, yeah. It was a good exercise, isn't it? Which you did. So I've sort of made two continuous edges continuous, and you can see how suddenly our moment has decreased by a lot, isn't it? Even with those point loads, it's still, we know that our 136 slab, so even if I change it to 1 and 2, our 136 slab will quite easily work. Yeah, makes sense?
Yeah.
So if we've got point loads, this is how you can, you can work your slab. You can eliminate, deep bed footings or board piers underneath these smaller, because they can be taken by your slab.
Mm-hmm.
Yeah. Our slab at 136 is sort of it's the minimum. You won't go anything less than 130. A lot of engineers are using 140, 150 as when it's suspended. We are pushing the limit. That's the absolute minimum. When I was at Berry Gale, there was one client who was pushing us to do 125, and we did it for them because they have been doing that for a long time, and so slowly we moved them to 130. Using 136 slab, if you can imagine, you've got 25 mil cover up at the top, and you've got 30 mil cover at the bottom. So 55 millimeters out of the 130 is taken, isn't it? So if you so 130 minus 55, you've got 35 mil in between the top of the reinforcement and the bottom of the reinforcement. So each reinforcement, 8 by 8, is 16 millimeters thick. So you've got 8 millimeters plus 8 top, which is 16, and the same thing happens at the bottom. So, and then you take away minus 32. So you've only got 43 millimeters in between the reinforcement, which is nothing, isn't it? It's less than 2 inches. And then when you consider the lapping of bars, so in some places you've got, there'll be another 16 mil. So in those locations, your concrete between the bars are only 30 mil. So that's the reason why we wouldn't go anything less than 130. The minimum we keep it at 130, and in cases we can go higher. We can start to change our slabs and make it 140, but it depends on more like case by case basis. Does it make sense?
Mm. Yeah.
So that's just a little rundown on two-way slabs. So at least when you guys are doing it, you know how to design two-way slabs.
Mm.
The other thing is board piers and pads. If you are looking at this is 200 kPa, we can also when we've got larger projects, we can also add this sheet in our design also. So for example, the project which Romit is doing, Skylark. So you can use this too, Romit. And so this gives you the capacity of your board piers. You can put your show report number and your board pier dimension of 450 and your pad footings and so forth. Does it make sense?
Mm-hmm.
The other one is bulk pier beams. Okay. So you know how we've got our pier and beam computation? Paul probably knows it's a Excel sheet. I don't know if Kelvin has seen that or not.
The Excel spreadsheet?
Yep, you've seen it too, isn't it? Yep.
Yeah.
So instead of using that spreadsheet, you can use this one over here too. If you're looking at your beam, which is 400 deep, beam width is 300, and your slab thickness is 130. We'll look at the reinforcement a bit later. And allowable bearing capacity is say 250. String friction, we'll leave it at 0. Pier dimension, circular. PSN2, yep, that's fine. So if we are designing, say, a 2-story house with tiled roof and the floor is coming onto it, and two stories of brickwork. So our first floor, so they have used 3 cube, 3 kPa. I'll put that as 0.5. It's lightweight, and 4 meters, 2 meter is the span. And let's make it say 4.5 meters of roof load. Your brickwork is say 2.73 plus 2, 5700 is your height, and that's 2.4 by 1.5. Your roof is that, floor live load, other live load, 1.5 by 1500. So whatever we have in the Excel spreadsheet, we've got something similar which is in here too. And next to this, he's given us the areas of the reinforcement. So we normally use 311 trench mesh, and we can double that up. So that would be 540. We can go over here. We can put the bottom reinforcement at 540, and top reinforcement, we can have single layer. So what we can do is we've got 2 layers of SL82, and so we can use, say, 1 layer. So that's 227 in 1 meter cubed is in 1 square meter you would have 5 bars, isn't it? In like 8 mil bars in each direction in 1 square meter. So if our beam is roughly 300 wide, so you can say 2 bars would roughly fall in that direction, isn't it? Which could help our moment. So if I divide 227 divided by 5, it's about 45 mil. So it's 45 square millimeters times 2 plus 270 plus another 45. So it's about 450, 445 of reinforcement. So let's do 450. Do you guys know how I got 450?
Yes.
Yeah. Okay. So by using that, we're getting to design our moment. So it's your beam works, your pier capacity doesn't work. Your reaction is quite high. So with something like that, if we are spacing it at 2.5 meters, it's for 2-story house, 2.5 meter doesn't work. So we can make it to 1.8. So it still doesn't work because it doesn't have enough capacity. In some cases, what we have is we can use some skin friction to increase the capacity. If we are building in a clay area, so what the rule is, this is just a thumb rule. 10% of end bearing is your skin friction. So I'm 1 meter embedment into clay is gonna give me that skin friction. So by doing that, at 1800, a 2-story, 2-story wall construction with quite decent loads, we can have our beam spaced at 1800. Make sense? So it answers your question too, Romit, isn't it? When the project you were doing. So your one, let's change your one similar to what you were doing is, we'll delete that. That's your 5.
Roof is 0.4.
Sorry.
Roof is 0.4.
And 4.5, which is sort of decent. And for a single-story house, we can, push it to 2.5 meters. And even with 0 skin friction, you're sort of still failing. It's pretty, 2.5 meters is 2 meters. 2 meters is the end bearing is the limitation. So if we've got a 250 kPa soil in here, 250 kPa is not really good. It doesn't help us. We could go another 500. Say let's do 20 skin friction and 500 into it. Then it helps. We push spacings to 2200.
Yeah, managing the capacity.
So our critical thing in here when we're designing a slab system which is fully supported on board piers is the bearing capacity of the piers. So that's the most critical. if we are founding just at 250 kPa, then and we're not going into the clay, it doesn't help us. But most of the time, they would recommend us about a meter into clay to achieve that 250 kPa, isn't it? Because on the clay, it's usually one. Make sense? So I can open up Skylark. Yeah, Skylark is Munit's project. So my project is a critical project. So when didn't even look at the soul report until we did
92, 2092.
And yeah, thanks for that. Did you put the soul report in here? Do you know if we put it in there?
Hold on. Just a second.
Yeah. Can you see my screen? Using this spreadsheet, we can start to use the other software. And, it's all together. So this one over here is flow slab is 3.1 kPa being 14.34. 0.2.
I have placed the soul report in the box now. You can have a look.
30.
That other dead load that you have put 2.4 by 1.5.
Yep.
That's from where that load 2.4 kPa.
So you used 3.12, isn't it? In there, and your slab is 1100, and use 3.1 and 2700. Yeah, 14.69. It's pretty close. So if we sort of use the similar figures, 0 and now we can push it. So you can see something wrong over here. 200 kPa. Okay, so it's sort of sitting at 60%. So I can make it at 2.5 meters, and it's sort of giving us sort of quite reasonable values. So you can see how it's very similar to what Romit has done. In his calc, it's giving us, 4 meters.
I guess that's for interior about field because we don't have external walls on it. And
over here, the top one is for exterior. Just looking at so the skin friction over here is looks like it's quite high. So 4.25, 2.5, so loads are fine. Capacity is 72. Our capacity over here. That's the capacity 450.
I think the safe distance that I achieved along with the beams was 2.8. 2.8.
And it was 2.8 stone, based on the moment capacity.
Mm-hmm.
Now I'm just looking at the reaction.
Okay.
So this is 78.6 and the capacity is 74.2. So the capacity is correct, but the reaction is slightly higher. 14. Everything else looks okay. 21.23. I have to work it out and see what it does. 6.231 total working. Oh, yep. Okay. It's different. Yep. So 16.92 and working and the working load. Okay. Yep. So what they have done is the other spreadsheet is done as a working load capacity. So the working load capacity is different. It's the old code when there wasn't any factors in it. Whereas with this one over here, this spreadsheet is designed for Ultimate. So I think what we should do is we should transition from that spreadsheet and start using the toolkit ones.
Okay.
So that
Sure.
we know that it's tried and tested, and there's so many engineers who are using it, and I'm sure they would have gone through and commented and corrected, and it helps everyone because it's a huge collaboration of engineers throughout Australia and New Zealand and wherever it's gone to. Yeah, so it's a trusted software. So I'll be more inclined to start using these softwares. And so just to sort of go through, and because you guys may not have used it, we should start to use this more often.
Yeah.
If we design our sleeper walls, I think we should start to look at these ones here too. It's pretty similar to what we do, and what we should do is we should design different cases of sleeper retaining walls using structural toolkit and create a like a section on Dropbox or on the server where we've got computations against a typical sleeper retaining wall height table. Is it making sense?
Yeah.
So that we don't have to redo the comp again and again. It's done, and it could be done between Kelvin and Romet. When we feel like we are slow, we can do computations for sleeper retaining wall, and you know how we've got that one sheet where we've got timber and steel sleeper retaining walls and a table.
Yep. Yep.
So we can justify that table using this software.
Okay.
Mm-hmm.
So the table and the drawings are there already, but then we can justify using it using those heights and spacings using this software. Then it reinforces our work. It also gives you guys confidence that whatever is in the table, it works. Does it make sense? So on a similar note, we should also do a design for timber deck and timber floor for the house.
Yeah.
You know how we've got that the schedule.
Mm-hmm.
So we can do that too. So it's just because you guys have been using it for so long, but because we are all under the pump all the time, we don't get to design it. We know, oh yeah, it's there. We'll just put it in. But at some point in our lives, we have to know and learn how to design it and push the limitation. It makes sense. So first, when you guys start to design it, you might think, oh yeah, it's not working, it's failing, or it's too conservative.
Yeah.
But the more you spend time, the more understanding, the more discussions we have between the four of us, the better it will become, and the more confidence we will have with with whatever we have in our system. Okay, so just going through this and the basement, retaining walls, post footing design, post footing design. Okay, this is something which you guys can also use. You know how Paul created that spreadsheet with the that's pretty good. So I actually like it, and it's quite handy when you're using shallow footings. But if you're designing really deep footings, like your timber post or steel post going into a board pier, this is the spreadsheet you can use. Does it make sense? So this particular shape works well when the footing is deep. But when the footing is not deep, then you've only got the triangular passive force acting on one side, and then your force is sitting at 1/3 the height. So it's similar to what Paul has done. Yeah. And I've actually asked the boys to also put in the timber post computation in there too, Paul, so that on one sheet, we can design the post and we can design the pad footing.
Yeah, I've updated over there.
Yep. Yeah. Okay. So I haven't seen it. Maybe we'll go through it together one of these days so that we all across it.
Okay.
And I think Kelvin has also done something on roof bracing, the capacities of different types. Yeah. Maybe what you can do is, Kelvin, if it's in a spreadsheet, you can expand that by putting like a drop down with different wind loads and different types of bracing also. So if you're using all the available types of bracing like 30.1.2, 25 by 0.8, all those bracings could be on the side as a drop down, and you can just choose and drop down, and it gives you the areas and everything, and gives you the capacity.
Okay.
So it's just to make. So there's a few things in there to learn. Is the first thing is you get confidence in what you're doing. Number two is you've created a tool for everyone to use, and number three, it looks professional instead of doing hand combs. It's something which is in there and ease of work. So whoever's doing it, and once it's checked and gone through me and Paul, then we can give it out to everyone to use. And within a in 5 seconds you've got your forces, and it gives you a 25 by 0.8 ms strap brace is adequate. Makes sense. So it's just building these systems to help us get through all of that. I'm just trying to see how we can use more and more of these software instead of going to the spreadsheet. So sometimes most of the time we can't. I think this section over here in terms of the footings, we were not using. We were pretty much using mainly just timber, steel, concrete. Very little of concrete. I don't think you guys. Yeah.
On slabs and pavement, I can see residential slabs just pop on it. Let's see if it does the rough slab for us.
So what this does is it's a different thing. I don't know if you've looked at this or not. Let's play around with articulated mesh linear slow slab with say 10 meters. Length is beam. So what this does is it actually gives you the overall, the hogging and sagging moments. And this is purely based on AS 2870. Maybe we can start to look at these and and see and check our limitations on what it is. It failing? Average beam center to center spacing is 4.8 meters, and which we sort of do in any case. Let's have a look at this. 25 meters. It reverses that, and we change it to 20. Look at the flow report. Flow report gives you the characteristic surface movement. What it does is, you can put all those values in there, and it helps you to determine. See, that's not correct. Average beam center to center spacing is 8.2 meters, which is not correct. Mm-hmm. So 25 is, they've divided it by roughly 3. Yeah, 7 meters. It's about 4 meters. Beam depth, find 100. Yeah, so I don't know how this works. I've never used it. Maybe explore a bit more in terms of the 2870 and see how this works.
Okay. Yeah.
You and Kelvin, if you want to spend some time to understand this sheet, it's a good thing. It's a good thing to know what a is doing and why it's failing. So it's failing because the effective is saving out 36. It's got a combination. Yeah, it's something I'm not familiar with. Maybe you guys look into this and help us understand. Okay. So is it something for you guys to look at some stage? And then this also gives you the tree, and we can also explore these too. If we see a series of trees, and we can say that this is what the height is. Based in Melbourne, it's in the climate soil classification. Then it gives you the YS value, and this YS value can be used in this section over here. Make sense? Yeah. So and then tree effect on piers. So if you got board piers on in a house, it also gives you the type of effect. We never look at it. I've never. I've sort of just on 0.75 of mature height. If a tree is close to our building and it's 0.75 times the height comes to our slab, we either put a roof area or put the system as as a raft slab, or sorry, as a boat pier or screw pile system. Makes sense. I don't think we've ever sort of used anything from here. You guys are pretty familiar with the
For,
timber.
for the slab that we were doing with a post on a 2-way slab, internal post.
Yep.
Uh, just like rectangular bed footings, do we also have to check that for punching shear?
The loads are quite small,
Okay.
and so your punching shear would not be, it won't be critical. So
Okay.
if you want to have a look at it and say just check that, and let's see, and your design shear is say 1.2 by 5, 1.5 by 5, so it's about say 15, and slab 130, and the depth is sitting on that's a bit closer to fitment. Here head no is 2. Okay, so normally say 4. So you can see by looking at that, your punching shear is not an issue. You look at your shear capacity in here. So your 5 is 36 kilonewton. And this one here is more for your beam. So that's why it's got legs in there. In our slab, we don't have any ligature. Does it make sense?
Yeah.
And the other thing which happens is, if you've got a steel column, obviously you have got a large load, so you put a pet footing or a board pier underneath that. But if it's a timber stud, what happens is the timber stud is actually sitting on a bottom plate, and that bottom plate also helps you distribute the loading.
Okay.
Does it make sense? So in that, you could probably say it's 300, and in one direction could be 90, and the other direction say 300, or even 450. That's how your timber is working. So you can see that the punching shear is not an issue. It becomes an issue when the loads are quite big. So if we increase that load to say 50 kilonewton, then it tends to be then we are getting close. You see, even by 90 by 90 and 50 kilonewton load is still not punching through it. Can you see that, Ronit?
Yeah.
So it's all of these things are valid. They're good questions to ask yourself. And when we're designing it, these are things which we should be considering. And it's good to consider, good to do it once. And if we wouldn't have done this exercise now, we wouldn't know that. Like I didn't know the actual capacity of the slab in terms of punching. But by raising that question, it is help, isn't it? So it's all of these questions are educational, and we should be prompting this in our head. The other thing is plain concrete. I don't know if you guys ever had a look at plain concrete. So so when we're designing our pet footings, you know how we put in minimum reinforcement down at the bottom, SL82 at the bottom?
Yeah, I have seen it.
In reality, Yeah, we don't even need that. Yeah, it's what it's doing is if you guys get a chance, go through this plain concrete section. A plain concrete has also got some moment capacity.
Mm-hmm.
Yeah, so without any reinforcement, it has got some moment capacity. So just by looking at this uh, YMU, see in here there's no AST.
Yeah.
So it's a concrete with the depth of 500 with a width of a meter has got that much capacity. So if I reduce this to 100, let's do 200. So see, a 200 concrete has got 7.6 kilonewton capacity on its own, and it's based on the flexural strength of concrete. So say there's one is your compressive strength, and then there's a like a tensile strength of concrete. So this 3.39 MPa is like tensile capacity of concrete without any reinforcement. So when we add reinforcement to it, we are adding 500 MPa or 400 MPa. Does it make sense?
Mm-hmm.
So it increases the capacity. So when we're looking at a footing design, and if the footing is 500 deep, we that's the capacity of that actual footing. So we shouldn't be having any. It shouldn't we shouldn't be putting any reinforcement in it, but we do just to be conservative. Yeah, makes sense.
Yeah.
Mm-hmm.
Yeah. So you can put all those things there. Okay, there was something else which Romit wanted to go through, and this is something which I went through with Kelvin.
Mm-hmm.
Is so we've got a building which is like a carport.
Yeah, is it Morinda?
Morinda and Romit asked me a question today also.
Okay, okay.
This Salman Madon, so what I'll do, so this is our building. This is building, and this is our freestanding carport. So if we've got our wind acting in this direction, and we've got wind in this direction.
Just hold on, Navina. I think I still see that toolkit.
Oh, sorry. I'm getting ahead of myself.
Yeah.
Okay. So you guys are on the right screen.
Yeah.
Yeah.
These screen sharing thing, we might have to put some reviews back that we should be able to share multiple screens at the same time, isn't it?
Mm-hmm.
It'll be good.
Yeah.
Oh, that's my wish, isn't it?
Yeah.
We all can have wishes.
Yeah. Yeah.
Okay. So when this carport or NL fresco, if you say, is tucked away in an existing house. So that's the existing house.
Yeah. That drawing is exactly to what I'm looking at the moment.
Yeah. So yeah, I'm sort of using your example, and it's sort of similar. It's sort of so this is you can use this in a lot of different situations, similar to Morinda and
Mm-hmm.
similar to what you are looking at, Romit.
Mm-hmm.
Uh, I'll just put in Romit's question over here too, so that you can see what Romit has done, which is it's good. Copy. For some reason, I can't copy. I'll share this on Teams so you can see what Romit was asking.
Yep.
Yeah. So we've got wind, and our most critical post in here is that particular post and this particular post, and in that direction. So if the architects have only given us a 90 by 90 post, a 90 by 90 post, it doesn't work for deflection in this case. Even if it's 3 meters from there to there, you would tend to struggle.
Yep.
And if you've got a fascia area of say 200, let's say your area equals say 200 millimeters by say, let's make it 3.2 by roughly. I don't know how much it is. 0.2, 0.32, 5.8, and 4, 6, about 2 point something. 6, 5.2.
0.25.
So that's the force which is being applied to these two posts. Okay, can you quickly put it on the spreadsheet which you guys did to see a 90 by 90 how it's behaving?
Yeah, yeah. I'm looking for that. So, 90 by 90. So what is the material? F7.
Would be F7 treated
Yeah.
fine, and height say 2.7.
Mm-hmm. 2.2. Deflection will fail.
Fails in deflection, isn't it?
Yeah, and
So
strength is
it
okay.
works, yeah, works with strength. It fails in deflection. So have you halved the load, 0.26, or is it full 0.26 load?
Oh, sorry, not yet.
Okay, so just probably
Uh,
put 0.15.
yeah, 0.15. You will still fail.
Still fails, isn't it? Yep.
Yeah.
A 90 by 90 F7 is very flimsy. So
Mm-hmm.
even if you are holding like a 3 meter post and it's lying horizontal and you try and push in the middle, you could feel the flex, and it's very flimsy. it's always a good idea. So okay, let's do another one. So if you put in 100 by 100, so what does it do now?
Okay. I'll share the results of the last one.
Okay.
Yeah, in the team. So yeah, it's okay now. So the deflection is 15 while the limit is 18.
Okay. Okay. So in freestanding post, we can also create like a little table in high wind areas, or like an N2 type condition.
Okay.
100 by 100 timber post would work, isn't it?
Mm-hmm.
In for these type of loading.
Yep.
So that's the sheet looks quite good. It's a good start. It looks professional. We've managed to put in a lot of things in here,
Yeah.
and it's functional. It does what we wanted to do, isn't it?
Yeah. And I'm creating the database of material also.
Okay.
Yeah.
Perfect. So the more we try and automate, the better it becomes for us, isn't it?
Yes.
And so between the three guys, and you guys are young, you've got more tech knowledge. I'm getting in towards the old side. So I need you guys to come up with these things. So Paul started off, and you guys can finish it off from here.
Yeah. Yeah.
So that looks good. Moment looks fine, and yeah. So petrol is not an issue. So in some instances, when we are in a situation like this, it's ideal to use 100 by 100 post, and at the same time put bracing in, like the step bracing.
Mm-hmm.
Step bracing helps us to transfer forces from the outside force over here back into the house. So in this situation over here, I wouldn't worry about this force because the whole thing gets taken by the house. It's only this section over here which I'm worried about.
Mm-hmm.
This section over here gets taken by the house. I wouldn't worry about it at all. It's only this post over here. So if we can learn and we can understand how this works, it it helps the cause. I'll share what Romit did in his. I'll share it in the teams.
Mm.
Create, complete issue. You guys share things on Teams. Oh yeah, now let's see this. Oh good. Great. Rob, is it coming now? Doesn't. Now it doesn't work. Ways where okay, I'll do it another way. Put it in my phone.
Shall I send it to our SBD Baba? Baba?
Roman, Roman, is it the one you sent me this morning?
Yeah.
Yeah, I can copy that here.
Okay.
Yeah. I'll send it to you. Just bear with me for 1 second. I've got it on my phone too. Okay, done.
Yeah. It's there.
Yeah.
So you can see what Romit has done. with his calculations. I think Kelvin is also familiar with this.
Mm-hmm.
It did something similar in Morinda.
Yes.
Is this 8 meters the stand? Oh, 3 meters. Yep. Okay. So it's pretty standard. You know, your verandas, your carports are around that sort of mark. So what you did there, Romit, is you know, with your strap bracing, with the angle, the calculations. I haven't gone through the whole calc, but it looks like you're on track. That's how I would design it. So you know, the idea of this is, you know, when someone's pushing that, this pulls it back, and then the force gets transferred in that direction into the house, and that's resisting it. That makes sense.
Mm-hmm.
If the wind is acting in that direction, then this member over here gets into tension, takes it back, uh, and then puts it back in the house. Makes sense.
Mm-hmm. Yeah.
So that, and the critical one is to show that we should have a member over here, because this member will work in that compression. So if you put a small member over here, say for example, if your rafters are, you know, 190, the other critical thing which needs to be checked is that that particular member should be checked for compression too. Does that make sense?
Mm-hmm. Mm-hmm.
If I just quickly go to the force, force is 0.2, angle force, and let me check a timber post. I'm just on toolkit, checking, and so yeah, I've just done a quick check of a 140 by 45 MGP 10 and effective length 3 meters in both directions, strong and weak. Dead load I've just put in 0.1. The live load is we put it on wind. Looks good. 0.3. Yep. So actually, Toolkit has actually got the facility in there to choose the type of loading to check compression load. I've done a quick check, and the capacity with the load is at 0.05. So yeah, so your timber rafter in this instance works quite well. I'll just do a screenshot and put it in here so that we can. And sorry, bear with me for a second. So you can probably see I've just done a quick rough calc, and 3 meter length of your rafter, 0.3 kilonewton compression from wind load, and my capacity is 0.05.
Mm-hmm. That's that point three is only when we have a very flat roof with a fascia, is it, or it's for a variable roof? with
No.
30 degrees.
I've only taken based on what we've calculated roughly.
Okay.
So our force over here is 0.26, and with the angles, just did a rough estimate.
Okay. Perfect.
What's your force over here? The angle force, which is transferred to the member, the bracing.
I had 1.29.
Okay. So how did you get 1.29? Oh, because you had gable roof, isn't it?
Yeah. It's a
Okay.
it's a 30
Okay.
degrees pitch in there.
Oh, okay. So it's a gable roof, and is it a truss roof or is it an open roof?
It's like the rafter, open roof.
Right. Okay. Okay. Yeah. So it's a bit more complicated with your one. I can put 1.5. I'll put 1.5 there too, and still my bottom chord has got a capacity of 0.25.
Okay. Perfect.
Does it make sense?
Yeah. So
And
since architect he hasn't shown that particular beam, so are we going to introduce that, or will assume that force to be transferred along with the rafter?
no, I think your one is slightly different. Let me just open up the project. And with Kelvin's project at Morinda, he had roof trusses. So had a flat ceiling in there.
Yeah.
And your project is which one is that?
It's 137.
37. Sorry, guys. So this is Enlight Building Design, isn't it? Yep. Okay. I'll just copy these drawings across so you can see that. Okay. So can you see my screen?
Yeah.
PDF, the points. Okay. So in your case, Romit,
Yeah.
should we open this up on Bluebeam? It's a lot better. All right. Well, we're almost done. Sorry for you're probably sitting there and gone bored. I'm learning too, believe me. All these questions you guys ask, I have to think, impromptu to try and answer you guys. Okay, so that's the having a quick look. Okay, just go through browsing through the elevation. Okay, so we've got something funny, fancy happening over here. I don't know what's that section there. And if you then cross section 3 to the other direction. Okay. So the other direction is just your. I think this is just a flat roof, isn't it? Which matches with that. So you've got a beam over here, beam over here, a beam over here, and a big ridge beam, isn't it? The way I would be designing that is, Romit,
Yeah.
is over here. is you probably put a beam there and a beam across over here.
Yeah.
And so your case is slightly different. And you would have a beam over here and a big beam running from there all the way to here.
Okay. Okay. So that beam in the front, we have to put that.
Yeah. So this beam is. I'll show you. I'll show you how it's done in elevation.
Mm-hmm.
So that's your rafter.
Mm-hmm.
The rafter over here.
Yeah. 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 Have done that. I've put those rafters there.
And then your rafter, which is this direction. And same thing happens like that.
Yeah.
And that's what it is. This is probably a big beam which you would have. And
Ridge beam. Yeah.
yep. And what you would have is your loading is this much loading. And your force would X like that, isn't it?
Yeah.
Yeah. So your case is slightly different. So I wouldn't be putting any bracing in there. What you have is you've got one post, two posts,
Mm.
three posts,
Yeah.
four posts,
5 posts.
5 posts. So your force of 1.27 or 1.5 is divided by 5 posts.
Mm-hmm.
Yeah.
So it's a different situation what you have. Does it make sense?
Yeah.
And
And
deflection is only 5.1 in this case.
it's nothing, isn't it?
Yeah.
Yeah.
So your case and what size post have you used?
100 by 100.
It's
Okay. The architects have said they want
1,
140.
140. Yeah.
Yep. So if you put 140, it's nothing, isn't it?
Yeah,
Yeah.
1.3.
And this is Mount Eliza high wind, which is quite critical. So that particular beam which I was talking about is we have to ask the architect what he means by these diagrams. Is it, it's something which he is, it's built with in terms of drawing. It's feature which they are, doing something on a sheeted end sheet, or are they creating a truss? Does it make sense?
Mm-hmm.
So that's something which we have to talk to him and find out. At the moment, the way he's showing this is that it's like a roof truss, and it's been designed like that. So that's your roof truss, and you've got a big ridge beam sitting, over here. Make sense?
Yeah.
Another alternative to doing this is you could have your rafter. You could have your rafter. You have a big beam over here. That's your main beam. And you've got a post.
Yeah. Yeah. On the ridge.
Yep. Oh, what the hell? Supporting ridge. So this is another way to do it. And then all of this force is then taken by
The beam.
all of them. And your advantage over here is that you've got a post which goes all the way down, like that. And a series of posts. And what you could have is you've got your bearer, which is sitting at this level over here. And you could also have, something over here where you could brace your floor system.
Mm.
And this is critical because what happens is that then your post is actually cantilevering from here. You know what I'm saying? Once you brace it to this point. So again, when we look at projects like this, plan view doesn't give you all the information. You have to understand, you have to look at the whole picture of how it's getting integrated with the building. Is it, on the ground? Is it above the ground? How far is it above the ground? And all of these things, which are quite critical in terms of, yeah. So it's just give me. So it's and this is again going back to what I keep emphasizing is that we can't look at just the floor plan. It doesn't give us the full picture.
Mm-hmm.
It's the way that your approach was correct, but it wasn't. It doesn't apply to this situation. So your calculations you were doing, it doesn't apply to that.
Okay. Yeah.
Does it make sense? It's totally different.
Yeah.
Because your bracing has to go over and go. It's not as effective when your bracing is in that plane.
Yeah.
When it's in this plane.
Mm.
Yeah. Your bracing has to be in that plane. I'll remove this. Yeah, it's got to be in that plane.
Mm-hmm.
Then you can transfer it properly. But in your case, it's not. It's sort of
No. Yeah.
yeah. It's at two different planes.
Yeah. It's
and your step bracing is not effective when it goes across because you can't get that tension to happen. And if you tension a lot, then what you're doing is you tend to put a lot of pressure on the ridge.
Mm-hmm.
You know what I'm saying? So if you can imagine, you fix something on this end, and you fix it on that end, and there's tension is in the middle.
Uh-huh.
So you've got reaction over here, reaction over here. There has to be some reaction in here too, isn't it, to resist that downward force?
Mm-hmm.
So you're putting undue pressure on your ridge beam. That makes sense?
Yeah.
So it's we have So not one size fits everything. It's got to be looked at case by case. The principle is correct, but it's not applicable to this particular project.
Yeah.
And then what we should, so before even, going into the design, we should understand the whole structure and ask questions to ourselves, what is happening in this area. The architect's cross section show us there's a ridge. And his ridge is so small, and his rafters are so big. We've got to ask him this question. We do a quick comp and check the size of the rafters and the ridge, and then we come to a conclusion and say, hang on, what does this give us? Then we go back and then we start to talk to the client, and then it's is it feasible? Does he want something? Does he want something like this? And so we just initiate that conversation. But without us looking at it, it's very hard to say, okay, I'm going to use a 300 dp. Then we can't go back and talk to someone. Do you know what I'm saying?
Yeah.
So it's it's a challenge. It's we have to have a look at the whole project. It's as a whole, individually. Just at the moment, I can see that you guys are only looking at the floor plan, elevations and cross sections. You're not building anything off that. Am I right in saying that? So we should be looking more in detail on how on the bigger picture, and try and build it in our head. This is how it will be built.
Okay. Yeah.
Okay. So does that help?
Yes.
Yeah. A lot.
Okay. Excellent. Thanks for that, and I'll email this to you guys now. So that what you can do is, if we had something like the process ST, then we could put this on there. So whatever we go through, and I think this is effective also, although it takes time. But in this time we've spent, there was a lot of learning, both ways, for you guys and for me too.
Yep.
Okay. You've recorded it with my voice there too. you can put it up on YouTube, the SBD YouTube. Okay, and then I'll put it on the SBD thing, LinkedIn.
Training, yeah. Yeah.
Yeah, so I can boast about my training skills.
Yeah.
Okay, all right. I'll leave you guys with it, and I think I have answered all your questions from it.
Yeah, you have.
Okay, sounds good. All right, I've got Joe waiting for me on the other line. He just sent me a message saying I was done 1.5 hours ago. I'm still waiting for you. So I'll get on and I'll have a chat to him now.
Sure.
All right, thanks guys.
Thank you.
I'll leave it with you guys. All right, see you. Bye.
Thanks.